Okay, so chain rule. So we talked about how we can find the derivative if we have two terms that are multiplied with each other. We go through product rule. And if we have two terms that are divided by one another, we go through quotient rule. Okay. But what if we have a function or an expression that is within another one? So composite functions. So if I have a function within another one, then we go through something called chain rule. So chain rule, we are going to involve the derivatives of both the outside and the inside functions. So, but we're taking turns with them. So let's say there's an f and g is inside the f function. Then our rule is we take the derivative of the outside expression, multiply by the derivative of the inside function. But the way that we do it is we take the outside derivative, but we leave the inside alone. That is the rule that we follow. Multiply by the inside derivative. So here are the steps. We take the derivative of the outside while keeping the inside portion unchanged. And then second, we multiply the derivative of the inside expression. So being able to go through something called chain rule is actually allows us to solve, find the derivative, find the slope formulas for functions that would otherwise be very difficult or impossible with the current methods that we have. So for instance, if you look at example 1 here, 3x squared plus 2 to the 5th, I mean, we can find the derivative using power rule, but what needs to happen first if we want to do a power rule with this?
You do actually outside.
Yeah, we gotta FOIL this out 5 times, right? And that is too much. That's too much to do, and you're not required to do that. I mean, we can go through various methods, but for our course, we don't have to worry about that. The only time we got to FOIL out is raised to the second power, not even the third power. Third power, we don't have to worry about that. So if anything's more than 2, we want to find a more efficient way of finding the derivative. So what if we can think of this as an inside and outside function? So and this is what I mean by that. Think of the outside function as what you see with the parentheses and what's outside the parentheses. So imagine there's an outside function that is parentheses to the 5th power. And then the inside portion is the 3x squared plus 2. So we're basically just going to take turns with each of these derivatives. Now, imagine the parentheses is like a variable. Imagine this is x to the 5th, right? What's the derivative of x to the 5th?
5x.
5x to the 4th. So imagine the parentheses is the x. What's the derivative of parentheses to the 5th power?
5 parentheses to the 4th.
Good. 5 parentheses to the 4th. So that represents your outside derivative. That is the f prime of g of x. We've created that. Now, what do you think goes inside the parentheses? Look at the formula here. What goes inside the parentheses? Yeah, the original inside expression. Okay, so we don't do the derivative just yet. I know it feels more efficient. Why not just get the derivative out of the way inside here? But that's not what the rule says. The rule says take the outside derivative, but leave the inside alone. And then the inside expression will have its own space to do the derivative. So times, what's the inside derivative? 6x. That is going to get its own space. It's not going to be within the outside. It's going to have its own space. So a lot more efficient. We'll get the derivative same way if we were to FOIL all this out, go through our power rule, combine like terms, factor it out. But we can get it all basically in one step. Okay. Now I can do a little bit of cleanup. I just like to push my coefficients together here, so or my linear expression. So I can push this out as 30x. And then parentheses 3x squared plus 2 to the 4th. So we keep learning these new derivative rules, but the big picture is the same. All this is doing is describing how the slope is changing at every point on this graph, right? It's a function, it feels more complicated, but our derivative is still acting the same way. It's just telling us how the slope of the original is doing.
Oh, so you You multiply the 6x with the 5, that's it.
Yeah, because these can combine together. I mean, it's,
So you treat them like they're separate, like, things. Like,
Yes.
you can't, like,
now these are the same thing. This is just the cleaner version of the top. Right, because I can multiply the 5 and 6 together. Remember, with multiplication, I can always rearrange terms however way I want to, right? The order, I'm not breaking any rules. Now, I can't distribute the 30x through the parentheses because the exponent is there. So this is as far as I can get in terms of factor form. All right. Now, this is what some students do, though. When they do derivative using chain rule, they want to do this 5, like I think some of you guys mentioned it, as 5 raised to the 4th, and they want to put the 6x in here. So we can't, I know this feels more efficient, but it's not the right way to do quotient rule, okay? Sorry, chain rule. We can't just put that derivative inside the parentheses. So the derivative is always going to have its own space outside, not inside.
So for the exponent, you can't like you have to forward it out. You can't like just put like a fourth root on every I mean a fourth exponent on every term.
We can, right? So it'd be nice, right, to just distribute that 4 through the parentheses. But if I wanted to do that, I'm missing a lot of things here. If I wanted to really FOIL this out, I got to write this out 4 times and actually distribute 4 times through, right? The only time I can distribute an exponent through is that there was no plus sign in between. For instance, let's say it was like 3x squared y to the 4th. There is no addition sign in here, so I can say 3 to the 4th, x to the 8th, y to the 4th. That's okay. I can distribute the exponent through if I don't see plus or minus. But as soon as there's an addition or subtraction, there's more to it than that. I can't just distribute the exponent through. Yeah. Okay, example 2, it says find all the values for the function for which f prime is equal to 0 and where f prime does not exist. But let's go ahead and find the derivative first, and then we'll talk about what this means. So we talked about how anytime we want to find the derivative of a function, it helps to rewrite it using rational form. So how can I rewrite this in a form that maybe is a little bit easier to work with?
X squared minus 1 squared to the 1/3.
Close, but is there, what else? What's a cleaner way of saying square to the 1/3?
You can multiply it 2 times 1/3.
Yeah, which is what?
2/3.
2/3, yeah. Okay, the exponent goes in the numerator. So root goes in the denominator. So we can't FOIL this out, right? We can't distribute, we can't clean this up. This is stuck in that form, but do you guys see an outside-inside portion? Yeah, so we can go through chain rule here, but I want to find the derivative. So the outside portion is whatever you see in with the parentheses and what's outside of it. And then the inside is obviously what you see inside the parentheses. So we can go through chain rule, take the derivative of each separately, and that will produce the slope formula, the derivative for our function. Okay, what's outside's derivative? We'll just go through power rule here.
2/3 to the first, or to the negative 5/3.
Remember, we're
Negative 1.
subtracting, yeah, subtracting 1, right? So 2/3 minus 3/3 is negative 1/3. Good. All right, what goes inside here? Good. X squared minus 1. We don't take the derivative just yet. Okay. The rule tells us not to do it, right? But we're gonna wait until it has its own space before we find the derivative. Okay, so x squared minus 1 goes inside times. Okay, now we're ready. What's this expression's derivative? 2x, right? 2x, x squared becomes 2x. The 1 goes to 0. Now, how can I clean this up with positive exponent and maybe just one fraction? How about this? Let's just figure out what goes in the numerator and what goes in the denominator. And that way we can, what can I put in the numerator? Good. The 2 and the x, they can all go together. They're all numerator terms. Okay. What goes in the denominator? Good. So that 3 is in the denominator. I'm just going to go ahead and leave that there. The x squared minus 1, I'm going to push it down, make it share the same space as the 3. So there's my slope formula. This is my derivative. Any questions? You could do a cube root. I'm just always going to leave it in rational form, but it's good to know the radical version of it, because on the AP exam, if the answer is in radical form, then you have to pick the radical form. But I'm just always going to leave it in rational form. If you did radical form on the quiz or test, that's fine. That's, it's just a different form. It's up to you.
Well, if you did radical form, like you put cube root on the bottom, what do you have to rationalize it?
No, this course, we don't have to rationalize the radical. You could rationalize, but you're just creating more work that you don't have to do. Okay, that's the first part. Find all the values where f prime is equal to 0. So can you rephrase it a different way? What does this mean?
Where the derivative does not exist.
Well, f prime doesn't exist. That's where the derivative doesn't exist. But can you phrase it a different way so that it feels slope is 0, right? So f prime equals 0. I know this feels abstract, but that just means, can you tell me where on the graph there's a slope of 0, right? So whatever the graph looks like, I just want to figure out where is my graph going to experience a 0 slope, where it's going to kind of flatten out for a moment. Okay, so anytime you want to find out where your slope is 0, you're going to set your derivative equal to 0, but there's a particular place to look if there's numerator and denominator. You're just going to set your numerator equal to 0 if you want to find out where the slope is 0. Now, in that vein, what do you think? Where do you think we can find where f prime does not exist, or where the slope does not exist? Good. We set the denominator to 0, because whatever causes the denominator to be 0 is where my slope is undefined, because I can't have a 0 in the denominator. So if I want to find slope 0, I set the numerator equal to 0. If I want to find a place where the slope is undefined, such as a vertical tangent, I set the denominator equal to 0. Okay, so I'm going to break it down here. So just set the numerator equal to 0 to figure out where my slope is going to have a horizontal tangent. And if I want to find slope undefined, I'm going to set the denominator equal to 0. So if I solve for x, this will tell me where on the graph is the slope going to be undefined. Okay, so here, divide both sides by 4, x equals 0. So when x equals 0, I'm going to have a slope. The graph is going to experience a slope 0 at this location. For this one, I can divide by 3. I can cube both sides. Basically, I can just get rid of all that. Divide by 3, cube both sides. Solve for x, I get plus or minus 1. So we have 2 locations where the graph is going to experience a slope undefined, 1 and -1.
Is there ever any case where it's like not for you, area where it's undefined?
That's true, yeah. So if there is no variable in the denominator, then there's no place where the slope is undefined. Obviously, if there's no variable in the numerator, that means there's no place where slope is 0. Okay. Yeah, so there has to be a variable there in order for us to find these locations.
So here, when I do this, let's like a fraction.
Exactly, yeah. You can't find slope undefined unless there's a fraction and the variable in the denominator. Okay.
But you find when it's 0 still, right?
If there's a variable up top, yes. Yeah. Right, if there's no denominator, you can still find slope 0. Just set your derivative equal to 0.
What is going to test one?
No, 3. Yeah, this will be on the test next week.
Okay. It's not a quiz, right?
Not on the quiz. Okay, 4 over x plus 2 squared. Find the equation of the tangent line. So I want to find the, okay, so every time we learn a new derivative rule, we're going to find the tangent line equation. So we have to find order pair, find the slope, and point slope form, right? Let's do the easy stuff first. How do I find the order pair? Into the original, right? So y of -3. Okay, so there's my order pair, -3, 4. I don't have to touch my derivative to get my order pair. Now, to get to my derivative, I could go through quotient rule, but is there another way that I can rewrite this equation and avoid the quotient rule? Right. What if we bring that 2 up to the numerator along with the parentheses? Then it's going to look like this. Everything is in the numerator. There's not even a need for a product rule because the 4 is just a number. It's just going to tag along to whatever this derivative is. But we definitely see an inside, outside, inside portion. So we have to go through what rule here? Chain rule. Yeah, there's an outside, inside portion. Obviously, we can't distribute the -2 through the parentheses. It's kind of stuck in that form. So outside is 4 parentheses to the -2, and the inside is the x plus 2. Okay, so what's the outside derivative here? -8 parentheses to the, good. What goes in here? No changes. Okay, we took care of the outside derivative. The inside derivative is going to be in its own separate space. What's x plus 2's derivative? This one. Okay, we have our slope formula. I'm going to clean this up and then use it to find my slope. Okay, how would you rewrite this with positive exponents? Good. The x plus 2 comes down. The -8 does not move with it. It stays up top. Now I can use my slope formula to find my slope.
You put us in place slope form.
Yep, now with point slope form. Yep. So we have our order pair. Which is -3, 4. Okay, questions so far?
So whatever says equation at tangent line, does that just mean point slope form? Equation?
Yeah. I would say, yeah, we just always leave it in point slope form. I mean, you could do it in general form or standard form or slope intercept, but I like point slope form because it's the fastest one, easiest one to get to.
Then you can find the point without finding before finding the derivative.
Yeah. Or we can do it after, but your point is just with the original function, though no derivative involved to find your point. Okay, example 4. This we obviously can tell this is not something that we want to expand. Write this out 3 times and go through, so we want to leave in this form. So there's obviously an inside outside portion. Again, chain rules involved here. Okay, what's the outside portion here?
Purposes of the term.
And the inside portion is
X minus 1 over x squared.
Yeah.
It's 4.
Okay, we do outside first. What does that become? What goes inside the parentheses?
X.
Yeah, whatever you see up here, right? Don't make any changes to it. Times, now we're ready for the inside derivative, but look at how this is set up. We're kind of forced into what rule here to find the derivative of this quotient rule. Yeah. Okay, F prime. G, no changes. Back to F. G prime. All over denominator squared, which is what?
X squared minus 16. X to 4 minus 16.
X squared minus 4 squared, right? So yeah, we don't want to square what's inside the parentheses. Just leave the exponent outside as you see it.
Can you say you could FOIL it if it's like to the second?
We could, but we don't want to, because if we do, we lose the ability to find things easier in the future. So unless it's x squared minus 4 squared and you're trying to find the derivative just using power rule, but if it's quotient rule, leave the denominator alone. This is set. This is where you want it to be. Now, clean up. I'm going to clean this up a bit. I'm going to distribute that through. So if I get x squared minus 4 minus 2x squared plus 2x, and that cleans up to be negative x squared plus 2x minus 4. Okay, so this is my cleaned up version of this mess that I have here. Now, this is the way that we can do it. So we can kind of have a relatively clean version of the derivative. Let's just identify all the numerators and put it there. Identify all the denominators and put it there. And then we can have all these in parentheses factored form. So tell me what goes in the numerator that you see.
X minus 1.
Okay. Well, first I see the 3, right? And then
X minus 1.
X minus 1 to the second. Okay. Remember, I can split this up, right? These are separate things here. And then I have the cleaned up mess that I have from the numerator there. So I'll put that there as well. Okay, what goes in the denominator?
The 3 as well.
Well, the 3 is up top. It's really a 3 over 1. So the 3 is just up top. Yeah, x squared minus 4. How many x squared minus 4 do you see? Squared. Okay. And this is also
X squared minus 4 squared as well.
Yeah. And can I combine these?
X squared minus 4 to the 4.
Yeah, I can add exponents. Okay. The thing that students get thrown off here is they want to say x squared minus 4 to the 3rd power. Why do you think that is? Instead of 4th, they want to say 3rd.
Because we to bring the second down.
Yeah, they forget to bring that 2. They see the 2 for the top, but they forget the 2 is also impacting the bottom. So they say x squared minus 4 to the 3rd, but it's actually going to be 4 down.
That's your answer.
That's my derivative. That's my slope formula for this, whatever this graph looks like.
So for the quotient rule, you like what's on the numerator, you distribute that so you combine like terms.
Yeah, so I want to distribute that just so I saw that this was relatively easy to clean up, so I went ahead and I cleaned it up a little bit. I want to get back to example 5, maybe tomorrow, but I want to spend some time continue to do quiz review. So if you guys can turn to page 46 in your packet, previous packet, sorry.
We have another quiz review for like Friday.
Friday, yeah, Friday morning, 7:15.
So we have like a third quiz review that we can do.
Oh, review worksheet? Yes, I'll give that to you tomorrow.
Oh.
Okay, let's see if we can see how much we can get through with page 46 here. Particle moves along the x-axis. So your particle motion problem will look like this page. Okay, so being through this page, that's really good because you'll get this problem, you'll get a quotient rule problem, you'll get 2 power rule problem. It's front and back. Okay, particle moves along the x-axis so that its position is given by x sub t. And we're only dealing with t values greater than or equal to 0, feet per second. Okay, include units with your answers. Find the velocity acceleration function. So just go through power rule, right? Position to velocity and velocity to acceleration. Okay, let's build the two functions here. So v of t equals, what would you say, derivative? Plus 15, right? And the 7 goes to a 0. Okay, all right, acceleration.
The derivative power rule that.
That's right. Power rule of velocity will get us to, or derivative of velocity will get us to acceleration. We get
16 minus 18.
And yeah, 15 goes away to 0. Okay. Okay, what is the velocity at t equals 2 seconds? How should do that? 2 into velocity. Units of measure, feet per second, right? What's the acceleration at 4 seconds? We can do what here? Yep. Plug 4 in for the t variable of my acceleration function. What's our unit of measure? Feet per second squared. Okay, this is the trouble spot that many students experience. Find the average velocity of the particle between 3 and 8. What is the formula for average velocity?
Function.
Yeah, change in position over change in time. We do not touch the velocity function, even though you see the word velocity there. So it's x of 8 minus x of 3 divided by 8 minus 3. Some students wanted to use the acceleration function. Some students remember that at velocity, you don't touch the velocity, so they go to acceleration. So that's not correct either. You want to use the function above it. Function of position function. Change in position over change in time gives you average velocity.
Oh, so you always put the bigger number up in front.
You don't have to. I like to do x of 2 minus x of 1 divided by 2. You can do x of 3 minus x of 8, but if you do that, you got to do 3 minus 8 below. But you'll get the same thing. Okay, so I know these numbers are a little hard to get to, but it'll be easier on the quiz. But x of 8, all it means is I'm just inserting 8 in for all the t's. So just to tell you what that value is, ends up being 49. X of 3, I'm just going to insert 3 in for all the t's of my position function. So 65 over 5, you can leave it like that, or you can reduce it to be 13 feet per second. Now, I know we didn't touch velocity, but it is still a velocity calculation, so our units of measure are still going to be distance over time.
So what position would always be like meet like that unit per second? Position?
Velocity is always units per second, or a unit distance over time.
What would position be though?
Position would just be feet or meters or kilometers, right? Just the distance. Yeah.
What if it's like speed and not velocity?
Speed and velocity will share the same units of measure.
Okay.
Yeah. All right. When is a particle at rest? What's another way of thinking particle at rest? Set velocity equal to 0. Yeah. So don't put t into the velocity function. Right. You're replacing the actual velocity variable with 0. Okay. And then solving for t. It says when, right? So you're looking for a t variable. Okay, so I'll just replace 0 in for v of t. I'm going to factor the 3 out as well. Multiplies to be 5, adds it to be -6. So particle is at rest, t equals 1 and t equals 5 seconds.
That what you said, velocity?
That one we use velocity because we're trying to figure out when the particle is at rest. Another way of saying rest is not moving, and not moving means velocity 0. Okay, when is the particle moving right? When is the particle moving left? The hint is let's create our velocity sign line, and then we'll test each interval, and then we can write our statement. So here's my velocity sign line. I do have a starting point, right? What's my starting point? 0, right? It says that t is greater than or equal to 0. So no negative numbers here. We're only dealing with 0 and greater. Right, so here we got to maybe deal with a fraction here. What number can I test between 0 and 1? 1/2, right? So I'll insert into, it's not too bad because we only care about collecting the signs. So 1/2, and for t, 1/2 minus 5 is negative. 1/2 plus, sorry, 1/2 minus 1 is
Negative.
2 negatives gives me positive. So we know that in this interval, this object is moving to the right. All right, plug 2 in, or here, I'm choosing a number that I find is easy. 2 in for t, 2 minus 5, 2 minus 1, positive, negative and positive gives me negative.
You plug 3 in that, but
Yeah, you can plug in 3, you can plug in 4, but I like to plug in numbers close to 0.
Okay.
That's just my preference. Okay, plug in 6, 6 minus 5, 6 minus 1, positive. Now, once you test your numbers, don't use them again. I see some students want to involve them in your intervals, but the whole purpose of those numbers is just to get the signs. After that, it doesn't serve a purpose anymore. Okay, so some students they want to involve the 1/2, the 2, and the 6 in their intervals of moving left and right. It's not going to play a role. Okay, when is a particle moving to the right?
0 to 1.
The reason is because velocity is what?
Positive.
It's greater than 0. Right now, there's something a little that's a little bit off about this answer, though. Can you spot it?
The union chart.
Yeah, I can do union or comma, doesn't matter.
Bracket.
Right, there's something about this here. T is greater than or equal to 0. We actually have to test what's happening at 0 because the object is already moving by the time that we start figuring out the time. So we can test it, right? If I plug 0 in for t, 0 minus 5, negative, 0 minus 1, negative. So 2 negatives gives me a positive. So that means at 0, this object's already moving to the right. So this needs to be a what? Bracket. Okay, when does a particle change direction? Yeah, 1 and 5. And the reasoning is because velocity changes signs. Yeah, you don't specify the direction or the order of direction change, just have to say that changes signs. Okay, these two I haven't talked about yet, so let's talk about what this is. Displacement. The way you find displacement is just your final position minus your initial position. And what I mean by final position and initial position just means wherever you end up and wherever you started, depending on whatever t-value they give you. So you don't play with velocity, just because we just want to figure out how far are you from where you want to compare with. So it's simply just x sub 6 minus x sub 2, and that's it. Some students, they want to do a divide by 6 minus 2, but then you're doing average velocity. Displacement is just x sub 6 minus x sub 2. Or if it's from 1 to 5, then it's x sub 5 minus x sub 1. You just want to figure out where you are compared to where you started. All right, so just to speed things up here, x sub 6 means I'm just going to plug 6 into the position function, and that number ends up being negative 25. X sub 2 ends up giving us negative 5. So it's okay to get a negative value. That just means that you're ending up to the left of where you started. Now, total distance requires some additional work. Let me talk about that. It says, what is the total distance from 2 to 6? So imagine when you do total distance, just imagine that you may be changing direction, but you're just counting your steps, right? So every step that you take is a positive value, right? If you go backwards, you're still counting it as a positive step. But we have to decide between 2 and 6, is there a change in direction between 2 and 6? Yes, at where? 5. So we have to find the location at 5 as well. So here's the trick. You're going to find the location at 2. You're going to find the location at 6. But what's different is we got to include the place where he changes direction, because we got to make sure that we're counting his steps when he goes backwards as well. So we got to find his location at 5 as well. So that is the additional step that is not required from displacement. Okay, I'm going to fill this in here. X sub 2 was negative 5. X sub 5, x sub 6 is negative 25. And x sub 5 is, in this case, negative 32. Okay, so let me talk about what we do from here. So imagine you are walking along a number line. You're starting at negative 5. You're going all the way to negative 25. Sorry, negative 32. And you're turning back and you're going to negative 25. So this is your steps. You're going from here to here. And then you're turning around and you're going from here to here. So how many steps would you take to walk from negative 5 to negative 32, assuming that each step you're going by integer value?
Negative 37.
Okay. Negative 20, negative 27, right? Now, we're talking about steps here. So how many steps would you take? 27. And the way that you would do that is you would do negative 32 minus negative 5. I know it's a little bit messier because it's negative numbers, but just imagine you're negative 32 minus negative 5, that gives you the distance, how many steps you've taken, and you're taking steps. So make sure that you keep track of it in your head there as a positive number. And then from negative 32 to negative 25, how many steps would you get from here to here? 7 steps. That's a positive number as well. So in total, how many steps have you taken? 34. That's your total distance. Okay, I haven't gone over that yet, but that's how you total.
How do you label that?
Yeah. Oh, just say feet. Yeah, feet. You took 34 steps, or in this case, 34 feet.
So be always like, how do you figure that out without drawing a number line?
You have to draw a number line.
Okay.
You have to, yeah. So make sure that you have a number line to show you that there's a change in direction, and you're only keeping track of the place where it changed direction, and then you just count your steps. Wherever you go backwards, then you have to make sure you stop there and count those steps. Yeah.
Why is it in feet and not, why wouldn't it be 34 like steps?
Oh, sorry. I've been using steps just as a visual, but the units of measure is feet, so that's why it's feet. I find that if I use the word steps, then students tend to not think in terms of negative, right? When you think of steps, it makes it more natural that, okay, everything is positive, regardless of which direction that I'm going in. Okay, these two I will save for tomorrow. I'll give you another review worksheet. We have to cover another section tomorrow, but I'm glad that we can still kind of work in these reviews, even though we're covering a new unit. Okay, there is homework, but I should prefer that you guys study. So maybe I'll push the homework to be due like next Monday or something. All right, come get your phones. Okay. Thank you.
So next Thursday, I'm looking at like on scholarship, there's I'm like not even get home till like 2 in the morning. Is there any way that on Friday I can maybe take the test at a later period, because I don't know.
Yeah, I mean, sure. If you're out all day, I don't mind if you just take it on Monday.
Well, I really don't want to film it. I don't know.
That's fine, yeah, so whatever is good with you,
So I
always
was like, I don't have a second.
yeah, you can take a step with my second grade class.
Okay.
Okay.
Thank you.
Okay. I didn't know what's going. That good. I was here. Thank you. Yeah.
Oh. Have you gone over like probably?
Yeah, we have. So increasing speed, we compare velocity and acceleration. And compare the signs.
Oh, okay.
And then for velocity increasing, you just look at acceleration, because this is asking about the rate of change in velocity.
So you plug this into the accelerator. You plug this in the wall.
It's a both, and the same signs mean speed increasing. If one is positive, the other is negative, then it's speed decrease.
Okay, all right, thank you.